Today we're going to design an algorithm from first principles that's going to allow us to solve linear programs with as many decision variables as we like and as many constraints as we like. So today we're going to design an algorithm from scratch to solve arbitrarily large linear programs. Okay? And we're going to design this algorithm on an example, but the principles that we're going to learn and develop are going to be applicable to any linear program that you would like to solve. Okay, so let's go ahead and design an algorithm that is going to allow us to solve arbitrarily large linear programs. Okay, so let's take a linear program. Let's take a linear program that looks like this. Maximize 3x1 plus 4x2, subject to a bunch of inequality constraints. So x1 plus x2 is less than or equal to 1000, x1 plus 2x2 is less than or equal to 1200. Let's say x1 is equal to 400, and x1 and x2 are non-negative. Okay. Let's design an algorithm that is going to allow us to solve this linear program. 2 decision variables, 3 inequality constraints, and our decision variables are restricted to be non-negative. The first thing that we're going to do in our algorithm is to express all of our inequality constraints as equality constraints. Okay, so the first thing we're going to do is we're going to express all of our inequality constraints as equality constraints. And here's how we're going to do it. Let me define W1 to be the amount, W1 to be the amount by which the right-hand side of the first constraint exceeds its left-hand side. So let's define W1 to be the amount by which the right-hand side of the first constraint exceeds its left-hand side. In a feasible solution to the linear program, the right-hand side of the first constraint has to be greater or equal to the left-hand side, which means that in a feasible solution to my linear program, the right-hand side of the first constraint has to be greater or equal to the left-hand side, so W1 has to be greater or equal to 0. So let me write down what I said. If x1 and x2 is feasible to the LP, then W1 has to be non-negative, and W1 is defined as how much the right-hand side of the first constraint exceeds the left-hand side. Okay, so that means that we can replace the first inequality constraint with W1 is non-negative, and W1 is defined like this. So the first inequality constraint is equivalent to writing W1 is non-negative, and W1 is defined like this. And equivalently, I'm going to write this definition by putting these terms to the left-hand side. Okay, we can represent the first inequality constraint as W1 is non-negative and this equality constraint. Let's do the same game on the second constraint. So let's define W2, the amount by which the right-hand side of the second constraint exceeds its left-hand side. In a feasible solution to our linear program, the right-hand side of the constraint has to be greater or equal to the left-hand side. So in a feasible solution to our linear program, W2 has to be non-negative. So now let's write down if x1 and x2 is feasible to the LP. Then W2 has to be non-negative, and W2 is defined in this way. So that means that we can replace the second inequality constraint by W2 is non-negative, and W2 is defined in this way. So the second inequality constraint can equivalently be written as W2 is non-negative, and W2 is defined in this way. And in this definition, let me do it again. Take these terms, throw it to the right-hand side, so that we write the definition of W2 in this way. Good. Do the same thing on the third constraint. Let's define W3 to be the amount by which the right-hand side of the third constraint exceeds the left-hand side. In a feasible solution to my linear program, the right-hand side has to be greater or equal to the left-hand side, so W3 has to be non-negative if x1 and x2 is feasible to the LP, and W3 has to be non-negative, and W3 is defined as this way. So that means that we can replace the third inequality constraint equivalently as W3 is non-negative and W3 is defined this way. And let's write this definition by throwing this term to the left-hand side. Okay. So now what we get from this discussion is that we can replace the first inequality constraint by this equality constraint and a non-negativity constraint on the W1 decision variable. We can replace the second inequality constraint by this equality constraint and a non-negative constraint on W2 decision variable. And we can replace the third inequality constraint by this equality constraint and a non-negative constraint on the W3 decision variable. Excellent. So now we can write our linear program with a whole bunch of equality constraints. Same objective function. But now, instead of this inequality constraint, let's use this equality constraint and a non-negativity on the W1 decision variable. But instead of the second inequality constraint, let's use this equality constraint and non-negativity on W2. And lastly, instead of this inequality constraint, let's use this equality constraint and non-negative constraint on W3. And in my original linear program, I had the non-negative constraints on the decision variables x1 and x2. We got to keep those non-negative constraints on our original decision variables. So now this linear program and this linear program are 100% equivalent to each other. Okay, so now we had these three inequality constraints. We expressed them as equality constraints plus these additional decision variables with non-negative constraints on them. These decision variables, these W's, have a name. They're called slack variables. They take up the slack in between the left and the right-hand side of each one of these constraints. That's why they're called slack variables. But again, this linear program with the equality constraints and the slack variables is fully identical to the original linear program that I would like to solve. So our algorithm is going to attack this linear program with equality constraints. Good. Good. So that's our first step. The first step in our algorithm is to write our linear program with equality constraints. The second thing we're going to do is we're going to express our linear program as a system of linear equations. We're going to have one linear equations for the objective function, and we're going to have one linear equations for each one of my constraints. So let's express our linear program as a system of linear equations. Here is the linear equation corresponding to my objective function, 3x1 plus 4x2. Let me set the value of the objective to be equal to some variable z. Here's my linear equation corresponding to the first constraint. Here's my linear equation corresponding to the second constraint. Here's my linear equation corresponding to the third constraint. Good. So express my linear program as a system of linear equations. One linear equation for the objective and one linear equation for each one of these constraints. So the system of linear equations captures all of the information in my linear program, the objective function and all of the constraints, and all of my decision variables are restricted to be non-negative, so I keep that information at the back of my mind. All of the x variables and w variables are all restricted to be non-negative, so let's never forget that, but I will not write those non-negative constraints in my system of linear equations. Okay, so now we expressed our linear program as a system of linear equations. There we go. So let's make now an extremely important on this system of linear equations. Let's make an extremely important observation. Let's make an extremely important observation on the system of linear equations. In this system of linear equations, there are three decision variables such that each one of these decision variables appears in a different constraint row with a coefficient of 1 and nowhere else. And those are W1, W2, W3. Let me say it again. In this system of linear equations, there are three decision variables, W1, W2, W3, such that each one of these decision variables appears in a different constraint row with a coefficient of 1 and nowhere else. Okay? Because of that very special structure, it's very easy to read a solution to this system of linear equations. Set W1 to be 1000, W2 to be 1200, W3 to be 400, x1, x2 to be 0. If x1, x2 to be 0, set z to be 0, and that's going to be a solution to the system of linear equations. Okay, so let's say that observation one more time. This system of linear equations has a very peculiar structure, which is that there are three decision variables such that each one of these decision variables appears in a different constraint row with a coefficient of 1 and nowhere else. And because of that structure, it's very simple to read a quick solution to the system of linear equations. Set W1 to be 1000, W2 to be 1200, W3 to be equal to 400, x's set them to be 0. If x's are 0, set z to be 0. That's going to be a solution to the system of linear equations. Okay. So that's very nice. So let's read the solution that we just quickly read. W1 to be 1000, we read. W2 to be 1200, and W3 to be 400, and x1, x2 to be 0. If x1, x2 to be 0, left is 0, so z is equal to 0, so that the first equation is also satisfied. Good. Is this solution that we quickly read to the system of linear equations, is this feasible to the linear program that we would like to solve? X's are 0, W1 is 1000, W2 is equal to 1200, W3 is equal to 400. X's are 0, W1 is equal to 1000, so 1000 equals 1000. X's are 0, W3 is equal to 1200, 1200 equals 1200. X's are 0, W3 is equal to 400, 400 equals 400. So this solution that we quickly read is feasible to the linear program that we would like to solve. If we actually look at the original linear program with the non-negative, with the less than or equal to constraints, it's still going to be feasible. X1 and x2 are 0. 0 plus 0 is less than or equal to 1000. 0 plus 0 is less than or equal to 1200. 0 is less than or equal to 400. So it's indeed feasible to the linear program that we would like to solve, however you read it. And the last thing I want to emphasize, last thing I want to check is, what is the objective value provided by the solution that I have? X1 and x2 are 0. X1 and x2 are 0, so the objective value is 0. So the value of the z variable corresponds to the objective value provided by the current solution that I have. Okay, good. So let's again recap ourselves where we're at. Let's again recap ourselves where we're at. We wrote down a linear program with equality constraints. We expressed our linear program as a system of linear equations. But this system of linear equations, this is very important, this system of linear equations has a very nice structure. In this system of linear equations, there are three decision variables such that each one of these three decision variables appears in a different constraint row with a coefficient of 1 and nowhere else. Because of that structure, it's very easy to read a solution to the system of linear equations. Set W1 to be 1000, W2 to be 1200, W3 equals to 400, x1, x2s are 0, set z to be 0. That's a solution to this system of linear equations. And this solution happens to be feasible to the linear program that we would like to solve with an objective value of 0. Okay. So now what we're going to do in our algorithm is that we're going to apply row operations to the system of linear equations. You know that when we apply row operations to a system of linear equations, the system of linear equations remains unchanged, remains equivalent. So we're going to apply row operations to the system of linear equations to get to other feasible solutions that give us better and better objective values. Okay? But the important thing is, as we apply row operations to the system of linear equations to get to other feasible solutions that give us better and better objective values, we'll always maintain the structure that there will always be three decision variables such that each one of these decision variables appears in a different constraint row with a coefficient of 1 and nowhere else. We'll always maintain that structure. That structure of always having three decision variables such that each one of these three decision variables appears in a different constraint row with a coefficient of 1 and nowhere else is very important. We're always going to maintain the structure. Okay. All right. So let's write down what we said. So we read the solution from the system of linear equations. This solution is feasible to the linear program. Is feasible to the linear program. This solution is feasible to the LP and gives an objective value of 0. Okay. So now we're going to apply row operations to the system of linear equations to get other feasible solutions that give us better and better and better objective values. And we know that applying row operations on a system of linear equations is completely benign. We will apply row operations to the system of equations to get to other feasible solutions that give better and better objective values. But as we apply row operations to the system of linear equations, we will always maintain the structure that there will always be three decision variables such that each one of these three decision variables are appearing in a different constraint row with a coefficient of 1 and nowhere else. We're always going to maintain that structure so that it'll always be very easy to read a solution to the system of linear equations that we face. As we apply the row operations, we will always maintain the structure that we'll always, I'm saying always twice, but that's okay. As we apply the row operations, we will always maintain the structure that we will always have three decision variables such that each one of these decision variables appear in a different constraint row with a coefficient of 1 and nowhere else. We will always maintain that structure. Let's go and do it. Let's go and do it. Let's apply row operations to the system of linear equations so that we get other feasible solutions with better and better objective values. But as we do that, we'll always have three decision variables such that each appears in a different constraint row with a coefficient of 1. Okay, let me copy the system of linear equations. So 3x1 plus 4x2 equals z. 4x1 plus x2 plus w1 equals 1000. x1 plus 2x2 plus w2 equals 1200. x1 plus w3 equals 400. This is the system of equations that we're starting with. Good. And now what is this? We have these three decision variables, each appearing in a different constraint row with a coefficient of 1. And what is the solution? We quickly read from the system of their equations. We said w1 equals 1000, w2 equals 1200, w3 equals 400, x1, x2 are 0. If then x2 are 0, z has to be equal to 0 as well to satisfy the first equation. But, so now I want to get to a better objective value. I want to get to a better objective value. The current solution is giving me an objective value of 0. I want to get to a better objective value. Let's look at the objective function row. Which variables values can I increase so that I can get to a better objective value? From this one, from the decision variable x1, for each unit of increase in the value of x1, increase the objective value by 3 units. For each unit of increase in the value of x2, increase the objective value by 4 units. So if I increase x1 or x2, I'm going to increase an objective value, so that's good. So increasing x1 and x2 is a good idea. But for each unit of increase in the value of x2, my objective function goes up by 4 units. For each unit of increase in x1, my objective function goes up by 3 units. It looks like x2 is giving me a bigger bang for my buck. So let's go ahead and increase the value of x2 to get to a better objective value. So we decided that we're going to increase the value of x2. We just make that decision by looking at the objective function row. We just look at the objective function row, increasing the decision variable x1. Each unit of increase the objective value by 3 units. Each unit of increasing the value of x2 increases the objective value by 4 units. Increasing x1 is a good idea. Increasing x2 is a good idea. But for each unit of increase in x2 gives me a bigger bang for my buck, so I just went ahead and decided to increase x2. You could have increased x1, your algorithm would still work. Okay? Okay, so now we decided that we're going to increase x2. We're going to increase x2. The next question we're asking ourselves is, how much can I increase x2 without violating the constraints in my linear program? How much can I increase x2 without violating the constraints in my linear program? And we're going to look at the constraints to answer this question. Let's get the first constraint. Right now in the first constraint, x2 is 0, w1 is 1000. x2 is 0, w1 is 1000. So I'm increasing x2. Right now, w1 is 1000, x2 is 0. As I increase x2, I'm going to eat up the increase in x2 by decreasing w1 so that they're still going to add up to 1000. Right now, x2 is 0, w1 is 1000. If I increase x2 to 200, w1 has to come down to 800 so that they add up to 1000. If I increase x2 to 600, w1 has to come down to 400 so that they add up to 1000. If I increase x2 to 999, w1 has to come down to 1 so that they add up to 1000. If I increase x2 to 1000, w1 has to come down to 0 so that they add up to 1000. If I increase x2 to 1001, w1 has to come down to -1 so that they add up to 1000. w1 is going to turn negative. That is infeasibility. So then what is the largest that I increase x2 before w1 turns negative? I can increase x2 all the way to 1000 before w1 turns negative. So from the first constraint, constraint 1 says you can increase x2 all the way to 1000 before w1 turns negative. So from constraint 1, we saw that can increase x2 up to 1000 before w1 turns negative. So that's the largest I can increase x2 from perspective first constraint before I run into infeasibility. Let's get second constraint. Right now in the second constraint, x2 is 0, which is the variable I'm increasing, and wt is equal to 1200. As I increase x2, I'm going to eat up the increase x2 by decreasing w2. Right now, x2 is 0, wt is equal to 1200. If I increase x2 to 300, so that this is 600, wt is going to come down to 600, so I add up to 1200. If I increase x2 to 350, this is going to be equal to 700. W2 has to be equal to 500, so that they are going to add up to 1200. If I increase x to 600, this is 1200. W2 is going to be 0, so that I add up to 1200. But if I increase x2 to 601, this is 1202, then W2 has to be negative, so that they add up to 1200. So the largest I can increase x2 is 600 just before W2 starts turning negative. So the second constraint says, constraint 2 says, you can increase x2 up to 600, which is given by 1200 divided by 2. That's 600 before W2 turns negative. What's happening in the third constraint? Does x2 appear in the third constraint? No. So then from the perspective of the third constraint, I can increase x2 as much as I want without violating any kind of feasibility. So the third constraint says you can increase as much as you want without violating feasibility. Let's say you can increase x2 as much as we want without, let's say, W3 turning negative. Okay, so the first constraint says we can increase x2 up to 1000 before we get in trouble. The second constraint says you can increase x2 up to 600 before we get in trouble. The third constraint says you can increase x2 as much as you want without getting in trouble. So then what is the largest we can increase x2 before we get in trouble? We can increase x2 all the way to 600. That's it, before we get in trouble. So the largest value we can increase x2 up to before we get in trouble is 600. So in this case, the mean value of x2 is defined by the second constraint. So we increase x2 up to the minimum of 1000 and 600. That is 600. In this case, the new value of x2 is going to be determined by the second constraint. Is determined by constraint 2. Let me write. The new value of x2 in this case is determined by constraint 2. So then we're going to do row operations such that x2 appears only in this constraint 2 with a coefficient of 1 and nowhere else. So do row operations such that x2 appears only in constraint 2 and nowhere else. So we're going to do row operations such that x2 appears only in the second constraint row with a coefficient of 2 and nowhere else. x2 has to disappear from the objective function row, s2 has to disappear from the first constraint row, and x2 has to disappear from the third constraint row, but it already doesn't exist now. Okay, so if I want x2 to disappear from the objective function row, I'm going to take the second constraint row, multiply by -2, add it to the objective function row, so that 2 times -2 is going to be -4x2 plus another 4x2, x2 is going to go away. So if I want x2 to go away from the objective function row, multiply the second constraint by -2, add it to the objective function row. And likewise, if I want x2 to disappear from the first constraint row, I'm going to take the second constraint row, multiply by -1/2, add it to the first constraint row. 2 times -1/2 is going to be -1x2 plus x2, that's going to be 0x2. So then we're going to take the second constraint row, multiply by -1/2, add it to the first constraint row. In this case, x2 is going to disappear from the first constraint row. Let's do those row operations and see what we get, where we get. Take the second constraint row, multiply by -2, add it to the objective function row. Let's do it. -2 times x1, -2x1, plus 3x1, just 1x1. -2 times 2x2, -4x2, plus another 4x2, 0x2, x2 disappears from the objective function row. That's the whole point of doing that. -2 times 0w1, 0w1, plus 0w1, 0w1, so no 0w1 on the objective function row still. -2 times w2, -2w2, plus another 0w2, that is going to give us -2w2. 0w3, -2 times 0w3, 0w3, plus 0w3, 0w3. Let's take care of the right-hand side. Keep z here. 200 times -2 is -2400. Add it over here, plus another z, z minus 2400. Right? 2400 times 1200 times -2 is -2400, plus another z, z minus 2400. So that's what we get, indeed, that's what we get in the objective function row. Let's take care of the row operations that we apply on the first constraint row. Take the second constraint row, multiply by -1/2, add it to the first constraint row. x1 times -1/2 is x1 times -1/2 is -1/2 x1 plus another 2. 2 minus 1/2, that is 4/2 minus 1/2, that is 3/2 x1. Good. Multiply this row by -1/2, add it to the first constraint row. x1 times -1/2 is -1/2 x1 plus 2x1, it's 3/2 x1. 2x2 times -1/2 minus x2 plus another x2, 0x2, x2 disappears from here. That's the whole point of doing that. 0w1 times -1/2, 0w1 plus another w1, that's a w1. w2 times -1/2, -1/2 w2 plus 0w2 -1/2 w2. 0w3 times -1/2, 0w3 plus another 0w3, 0w3. And on the right-hand side, 1200 times -1/2 is -600 plus another 1000, 400. Good. We're not going to apply any row operations on the third constraint row. Let's write it as it is. Lastly, we want x to appear in the second constraint row with a coefficient of 1 and nowhere else. So we're going to multiply the second constraint row by 1/2 so that x2 appears in the second constraint row with a coefficient of 1/2. So multiply the second constraint row by 1/2. Multiply everything 1/2 throughout. That is the new system of equations that we get. Good. In the new system of equations that we get, we have 3 decision variables such that each one of these decision variables appears in a different constraint row with a coefficient of 1 and nowhere else. Do we? Yes. W1, X2, and W3. We have 3 decision variables such that each one of these decision variables appears in a different constraint row with a coefficient of 1 and nowhere else. Because of that, we can again very quickly read a solution to the system of linear equations. What is that solution? Set W1 to be 400. Set X2 to be 600. Set W3 to be 400. Set X1 and W2 to be 0. If x1 and w2 are 0, the left-hand side of this equation is 0, so then z should be equal to 2400 to satisfy the first equation. So that is the quick solution that we read from the system of linear equations. Is this solution that we're reading feasible to the linear program that we would like to solve? Let's check it against the linear program with the inequality constraint. x1 is 0, x2 is 600. 0, 600. 600 is less than or equal to 1000. We're good. 0, 600. So this is a 1200 on the left-hand side. 1200 is less than 1200. x1 is 0. 0 is less than 400. Indeed, the solution that we get again in this from this system of linear equations is still feasible to the linear program that we're solving. And lastly, what is the objective value provided by the solution? x1 is 0, x2 is equal to 600. x1 is 0, x2 is equal to 600. So the objective value provided by the solution is 2400. The value of the decision variable z is also giving me the objective value of the current solution that we have. So now what did we do? In the previous system of equations, we had a solution that gave us an objective value of 0. Now we reached another feasible solution that gives us an objective value of 2400. We made progress. We're obtaining a better objective value. Okay. So now let's keep making progress. Is there another decision variable? Are there any decision variables that I now can increase to get to a better and better and better objective value? In order to answer that question, we're going to look at the objective function row. Okay. For each unit of increase in the value of x1, the objective goes up by 1 unit. So it's a good idea. If I increase x1, I'm going to get to a better objective value. Wonderful. On the other hand, for each unit of increase in W2, there is a -2 here. For each unit of increase in W2, the objective function is going to go down by 2 units. So increasing W2 is not a good idea. But still, I can increase x1 to get to a better objective value. So there's a decision variable that I can increase to get to a better objective value. So then let's decide that we're going to increase x1 now. Good. The next question we're asking ourselves is, how much can we increase x1 before we run into infeasibility? What is the largest we can increase x1 while still maintain feasibility? Let's look at what constraint 1 says. Let's look at what the first constraint says. Right now, the current value of x1 is 0. I'm increasing x1. And the current value of w1 is 400. So as I increase x1, I'm going to eat up the increase x1 by decreasing w1 such that the sum is going to still add up to 400. So how much can I increase x1 without w1 turning negative? So right now, x1 is 0, w1 is 400. If I increase x1 to 100, so the 100 times 3/2, that's going to be 150. W1 is equal to 250, so that their sum is going to be 400. If I increase x1 to 200 times 3/2, that's going to be 300. W1 is going to be equal to 100, so that their sum is going to be equal to 400. If I increase x1 all the way up to 800 divided by 3, 800 divided by 3 times 3/2, 800 divided by 3 times 3/2, this is going to be 400. Then W1 is going to be equal to 0, so that they add up to 400. So the largest x1 can go up to before W1 turns negative is, the largest x1 can go up to before W1 turns negative is 800 divided by 3. If x1 goes larger than that, then W1 has to turn negative. So then from the first constraint, can increase x1 up to, and that 800 over 3 is given by 400 divided by 3 over 2. That is 800 divided by 3. Then increase x1 up to 800 divided by 3 before W1 turns negative. If x1 is increased up to 800 divided by 3, this is going to be 800 divided by 3 times 3 over 2. That's going to be 400. W1 is going to snap to 0, so that they add up to 0. They add up to 400. But if you increase x1 a little bit more than that, W1 has to turn negative. Okay, so from the first constraint, we can increase x1 all the way up to 800 divided by 3 before W1 turns negative. What's happening in the second constraint row? Right now in the second constraint row, I'm increasing x1, and x2 is 600. So this is 0, this is 600. If I increase x1 to 400, then 400 divided by 2 is 200. Then this has to be 400, so that they add up to 600. If I increase x1 to 1000, so then this is 500, this should be 100, so that they add up to 600. If I increase x1 all the way to 1200, so then this is 100, x2 has to be 0, so that they add up to 600. So the largest x1 can go to before x2 turns negative is 1200. So from second constraint, can increase x1 up to, let's again write it as 600 divided by 1 over 2, which is 1200, before x2 turns negative. Wonderful. And what's happening in the third constraint? So right now in the third constraint, we're increasing x1, W3 is 400. Any increase in x1 is going to be eaten up by W3. How much can I increase x1 before W3 turns negative? This is 0, this is 400. If I increase x1 to 400, W3 is going to be equal to 0, so that they add up to 400. But if I increase x1 to 401, W3 has to be negative 1, so that they add up to 400. So the largest increase x1 can go to before W3 turns negative is 400. The third constraint says can increase x1 to 400 before W3 turns negative. Good. Constraint 1 says you can increase x1 up to 800 divided by 3 before we get in trouble. Constraint 2 says we can increase x1 up to 1200 before we get in trouble. Constraint 3 says we can increase x1 up to 400 before we get in trouble. So what is the most binding? This is like 266,666. This is 1200, this is 400. The binding is constraint 1. So we can increase x1 all the way to 266.666, 800 divided by 3, before we start getting in trouble, so that we're going to increase x1 all the way up to 800 divided by 3. So the new value of x1 is determined by constraint 1. So we're going to go ahead and increase x1 up to the minimum of 800 divided by 3, 1200, and 400. And that minimum is 800 divided by 3. So in this case, the new value of x1 is going to be determined by constraint 1. The new value of x1, is determined by constraint 1. That means that we're going to do row operations such that x1 appears only in the first constraint row with a coefficient of 1 and nowhere else. So row operations such that x1 appears only in constraint 1 with a coefficient of 1 and nowhere else. You want to make sure x1 appears only in the first constraint row with a coefficient of 1 and nowhere else. Let's do those row operations. I want x1 to disappear from the objective function row. So then I need to take the first constraint row, multiply it by -2 over 3, -2 over 3, and add to the objective function row so that x1 disappears from the objective function row. And likewise, I want x1 to disappear from the second constraint row. So I can take the first constraint row, multiply it by minus 1/3, and add it to the second constraint row so that x1 disappears in the second constraint row as well. And I also want x1 to disappear from the third constraint row. So I can take the first constraint row, multiply it by minus 2/3, and add it over here so that x1 disappears from the third constraint row as well. So let's do those row operations. Let's do those row operations and see where we get. Multiply the first constraint row with minus 2/3 and add it to the objective function row. Good. 3/2x1 times minus 2/3 minus x1 plus another x1, 0x1, x1 disappears. This is exactly what we wanted. 0w2 times minus 2/3, 0w2 plus another 0w2, 0w2, w1 times minus 2/3, minus 2/3 w1 plus another 0w1, minus 2/3 w1 in the objective function. What else? Minus 1/2 w2 times minus 2/3, that is going to give us plus 1/3 w2. Plus 1/3 w2 minus another 2 w2. So minus 1/2 w2 times minus 2/3, that's going to give us plus 1/3 w2. Another minus 2 w2, that is 1/3 minus 6/3, that is minus 5/3 w2. Good. 0w3 times minus 2/3, 0w3 plus another 0w3, that is going to give us 0w3. Let's take care of the right hand side. 400 times minus 2/3, that is minus 800 divided by 3, plus another minus 2400, minus 2400, minus 800 divided by 3. So this minus 2400 is minus 7200 divided by 3, another minus 800 divided by 3, so that's going to be minus 8000 divided by 3. C minus 8000 divided by 3 on the right hand side. Good. We took care of the objective function row. Let's take care of the second constraint row. Multiply the first constraint row by minus 1/3, add it to the second constraint row. Let's do that. 3/2x1 times minus 1/3, that is going to be minus 1/2 x1, plus 1/2 x1, 0x1, x1 goes away. That's the whole point of doing this. 0x2 times minus 1/3, 0x2, plus another x2, that is an x2 in the second constraint row. w1 times minus 1/3, minus 1/3 w1, plus 0 w1, minus 1/3 w1, minus 1/2 w, minus 1/2 w2 times minus 1/3, plus 1/6 w2, plus another 1/2 w2, 1/6 plus 1/2, 1/6 plus 3/6, that's 4/6. That is 2/3 w2. Good. 0w3 times minus 1/3 is 0w3, plus another 0w3, 0w3 over here. What do we get on the right-hand side? 400 times minus 1/3, minus 400 divided by 3, plus another 600. 600 minus 400 divided by 3, that is going to be 1800 divided by 3 minus 400 divided by 3. That is 1400 divided by 3. Good. Let's take care of the third constraint row. We're going to take the first constraint row, multiply by minus 2/3, add it to the third constraint row. Let's do those row operations. 3/2x1 times minus 2/3, that is minus x1, plus another x1. x1 goes away in the third constraint row. That's what we're doing. 0x2 times minus 2/3, 0x2, plus another 0x2, 0x2 over here in the third constraint row. w1 times minus 2/3, minus 2/3 w1, plus another 0w1, minus 2/3 w1, minus 1/2 w2 times minus 2 over 3. That is going to give us plus 1 over 3 W2 plus 0 W2 plus 1 over 3 W2, 0 W3 times minus 2/3. That's 0 W3 plus another W3, W3. On the right-hand side, 400 times minus 2 over 3 minus 800 divided by 3 plus another 400. 400 minus 800 divided by 3. So that's 1200 divided by 3 minus 800 divided by 3. That's 400 divided by 3. And lastly, we want x1 to appear in the first constraint row with a coefficient of 1 and nowhere else, which means that we're going to multiply the first constraint row across by 2 over 3, such so that x1 appears in the first constraint row with a coefficient of 1 and nowhere else. x1 plus 2 over 3 w1 minus 1 over 3 w2, 400 times 2 over 3, 800 divided by 3. Okay. Great. So this is the new system of linear equations that we got. Once again, we have 3 decision variables such that each one of these decision variables appears in a different constraint row with a coefficient of 1 and nowhere else? Do we? Yes. x1, x2, w3. So then we can read we can very quickly read a solution to the system of equations that we have. Set x1 to be 800 divided by 3. Set x2 to be 1400 divided by 3. And set w3 to be 400 divided by 3. And set w1 and w2 to be 0. And set z to be 8000 divided by 3. That's a solution to the system of linear equations that we have on this page. Great. Is this solution feasible to the linear program that we would like to solve? Is this solution feasible to the linear program that we would like to solve? 2x1 plus x2, 800 divided by 3 times 2, that's 1600 divided by 3, plus another 1400, that's 3000 divided by 3, that's 1000 is less than or equal to 1000. Good. How about this one? x1 plus 2x2, 800 divided by 3 times 2 times 1400 divided by 3, 800 plus 2800 divided by 3, that is 3600 divided by 3. 3600 divided by 3 is 1200. 1200 is less than or equal to 1200. We satisfy this constraint as well. x1, 800 divided by 3, that's 266.666. That's indeed less than or equal to 400. So this solution is feasible to the linear program that we would like to solve. We can also check that it gives us an objective value of 8000 divided by 3. So then in the previous iteration, we had a solution that was giving us an objective value of 2400. Now we got a solution that's giving us an objective value of 8000 divided by 3, which is 2666. So from 2400, we went up to 2666. We made progress. Great. So now, can we get to an even better objective value? Is there any decision variable that we can increase? Are there any decision variables we can increase to get to a better and better objective value? We look at the objective function row. If for each unit of increase in W1, the objective function is going to go down by minus 2/3. For each unit of increase in W2, the objective function is going to go down by minus 5/3. So there is no decision variable that we can increase to get to a better solution. So we can claim victory. This solution that we obtain is the optimal solution to the linear program that we would like to solve. There is no decision variable in the objective function row whose value we can increase to get to a better objective value. For each unit of increase in W1, the objective function goes down by minus 2/3. For each unit of increase in W2, the objective function goes down by minus 5/3. So there is no decision variable whose value we can increase to get to a better solution. As a result, this is the optimal solution to the linear program that we would like to solve. So let's write down our final solution. The solution x1, x2. Let me write the selects as well. The solution x1, x2, w1, w2, w3. x1 is 800 divided by 3. x2 is 1400 divided by 3. w1 is 0, w2 is 0, w3 is 400 divided by 3, is optimal. the LP. Let's also put stars here to emphasize that this is an optimal solution to the linear program that we're solving. Is optimal linear program with the optimal objective value, with optimal objective value 8,000 divided by 3. This is the algorithm. This is how we get to the optimal solution. We start from a system of linear equations. We apply row operations to get to other feasible solutions that give us better and better objective values. But as we do so, we always make sure that there are always 3 decision variables such that each one of these decision variables appears in a different constraint row with a coefficient of 1 and nowhere else. Okay, good. So now, this is the algorithm. And this algorithm that we constructed, that we looked at today, that we built just today, right now, is called the simplex algorithm or the simplex method. Okay, and we're going to do many examples on the simplex method to really nail down the mechanics of this algorithm. This was just our first example. In the next lecture, we're going to do another example. So we're going to keep on doing these mechanics so that these kinds of row operations to get to better and better feasible solutions is really going to be ingrained in your hands and in your brains, in your whole being. Okay, good. So now let's look at the solutions that is visited by our algorithm. We started from this system of linear equations, and we had this solution. And then after that, we get to this system of linear equations, we get this solution. And then we get to this system of linear equations, we got this solution. Let's sort of pictorially look at those solutions that we visited along the way. Here's the linear program that we wanted to solve. Maximize 3x1 plus 4x2, subject to 2x1 plus x2 is less than or equal to 1,000, x1 plus 2x2 is less than or equal to 1,200, and x1 is less than or equal to 400. My decision variables are non-negative. This is the linear program that we were solving. Let's plot the set of feasible solutions for this linear program, and let's see what solutions our algorithm visited during the course of its iterations. Let's plot the set of feasible solutions to this linear program. X1, X2, (200, 400, 600, 800, 1,000, 1,200, 200, 400, 600, 800, 1,000, 1,200. Let's plot the set of x1, x2 pairs that satisfies the first constraint. We know that in order to do that, I got to look at this constraint as I got to plot the line that represents this constraint. And let's plot that line. When x2 is equal to 0, x1 is going to take value 500, right over here. When x1 is 0, x2 is going to take value 1,000, right over here. So this is the line, this is the line, this is the line. So x1 plus x2 equals 1,000. The points on one side of this line is going to satisfy 2x1 plus x2 is less than or equal to 1,000. The points on the other side of the line is going to satisfy 2x1 plus x2 is greater or equal to 1,000. Let's take a test point to see which side satisfies the constraint in our linear program. Again, origin is a convenient test point, 0, 0. x1, 0, x2, 0. 0 is less than or equal to 1,000, indeed. So the origin side of this line satisfies my first constraint. So I want to satisfy my first constraint. I want to be towards the origin side of this line. I want to be towards the left and below of the first line. Let's plot the set of points that satisfies the second constraint. So let's plot the line that corresponds to the second constraint. x1 plus 2x2 equals 1,200. Let's plot this line, x1 plus 2x2 equals 1,200. When x2 is 0, x1 is going to be 1,200. When x1 is 0, x2 is going to be 600. So this is the line, this is the line. corresponding to the second constraint. Again, let's take a test point to decide which side of the line we should be to satisfy the second constraint. Origin, 0 plus 0 is less than 1200. Indeed, 0 plus 0 is less than 1200. The origin side of this line satisfies the second constraint, so I want to be below and to the left of the second line to satisfy the second constraint. Let's plot the line corresponding to the third constraint. X1 equals 400. That is going to be a vertical line. Let's see which side of this line I should be at to satisfy this third constraint. My test point is 0. Is 0 less than 400? Indeed. So I want to be to the origin side of this line to satisfy the third constraint. So I want to be below to the left of the first two lines, to the left of the third line. So I want to be below to the left of all of those lines. I gotta be here. Below and to the left of all of those three lines. Below and to the left of all of those three lines. Okay. And likewise, I want x1 to be greater than or equal to 0. So I want to be to the right of the vertical axis. And I want x2 to be greater than or equal to 0. I want to be above the horizontal axis. So then this is the set of feasible solutions to our linear program that we want to solve. Great. So now, this is the set of feasible solutions to the linear program that we would like to solve. So now let's plot the sequence of points that is visited by our simplex algorithm during the course of its iterations. Here is the system of equations in the first iteration. Here is the system of equations in the first iteration. What is the solution we had in the first iteration? X1 equals 0, S2 equals 0. So this is the system of equations in the first iteration. The solution that we had, X1 equals 0, X2 equals 0. Where is that solution? X1 equals 0, X2 equals 0. This is the solution that we had in the first iteration. Here is the system of equations that we had in the second iteration of the algorithm. What is the solution that we have in this solution, in the system of equations? X2 is 600, X1 is 0. X2 is 600, X1 is 0. X2 is 600, X1 is 0. It's that point. And this is the system of equations that we obtained in the third iteration. And in this solution, what is X1? 800 divided by 3. X2 is 1400 divided by 3. And if you do the arithmetic carefully, that solution turns out to be this one. 800 divided by 3 is like 266. It's right around 266 that you can see over here. And you can check the value of X2 as well if you just take the intersection of these 2 points. So what did our algorithm do? It started from one corner point of the set of feasible solutions. It moved to another corner point, and it moved to another corner point, and then it detected that this is the optimal solution to our linear program. Okay, so this algorithm that we constructed today, what it's doing is it's moving from one corner point of the set of feasible solutions to another corner point, to another corner point, to another corner point, until it detects that the corner point that is sitting at is the optimal solution. Okay, so when we were talking about the graphical approach for solving a linear program, we gained the intuition that an optimal solution to a linear program is going to occur at a corner point of the set of feasible solutions. And this algorithm that we develop is indeed visiting the corner points of the set of feasible solutions until it detects that the corner point that is sitting at is the optimal solution to the linear program. Okay, good. So this is the algorithm to solve large linear programs, and you can apply this algorithm to a linear program with as many decision variables and as many constraints as you like. In the next lecture, we're going to do another example on this algorithm so that we really nail down the dynamics of this algorithm really, really well. Okay, and let me say one last final word. This was the final system of equations that we reached. This was the final system of equations that we reached. And when we looked at this final system of equations, we said that there is no decision variable to increase that is going to make the objective value larger, so that we can conclude that this is the solution that we're getting it from the system of linear equations is the optimal solution. That is a reasonably satisfactory answer, but let me also try to give you a better, more satisfactory answer to conclude that this system of linear equations is actually characterizing an optimal solution. How can I conclude that this is indeed an optimal solution to my linear program? Let's try to think about that a little bit more carefully. And let me write that argument down at the second part of this page. My initial system of linear equations was this. And let me focus on the objective function rho. The objective function rho looked like this. Z equals 3x1 plus 4x2. Okay. By looking at this objective function rho, I don't know how much can I increase x1 and x2 to make my objective value as large as possible while making sure that I still remain feasible. But let's look at the objective function rho that we reached in the last iteration. Let me throw this 8,000 to the other side. The objective function rho that we reached in the last iteration is z is equal to 8,000 divided by 3 minus 2 over 3 W1 minus 5 over 3 W2, right? This is the objective function rho that we reach at the final iteration. And since this objective function rho is obtained from this objective function rho, they're all equivalent, right? Okay. If I look at the first objective function in the first iteration, I cannot really tell how much can I increase x1 and x2 to make my objective value as large as possible. But if I look at this objective function rho, my objective value is given by 8,000 divided by 3 minus 2/3 times W1 minus 5/3 times W2. And W1 and W2 are non-negative decision variables. Okay. So then the largest possible value of my objective value is going to be when W1 and W2 are as small as possible. Right? W1 and W2 are non-negative decision variables. My objective value is given by 8,000 divided by 3 minus 2 over 3 W1 minus 5 over 3 W2. So W1 and W2 are non-negative decision variables. So the largest value of my objective value is going to be obtained when W1 and W2 take their smallest possible values because they have negative objective function coefficients over here. Since W1 and W2 are non-negative decision variables, the smallest values they can take are 0. So then my objective value from this last objective function, we can conclude that my objective value is going to be at most, my objective value is going to be at most 8,000 divided by 3, because my W's are going to take non-negative values. When my W's take non-negative or positive values, it's only going to get smaller. The objective value is only going to get smaller. So from the last constraint, last objective function rho, we see that the objective value can at most be 8,000 divided by 3. And in the last iteration, we got a solution that gives us an objective value of 8,000 divided by 3. Hence, it's got to be optimal. Okay, so that is another structural, a systematic way of comforting ourselves that when we reach this final system of equations, the solution that we obtain is the optimal solution to the linear program that we would like to solve. Okay, so again, to iterate, in the last system of equations that we reach, the objective function rho reads as z equals 8,000 divided by 3 minus 2/3 W1 minus 5 over 3 W2. Okay. And my decision variables W1 and W2 are non-negative, and they have negative coefficients over here, which means that z's largest value is going to happen when W1 and W2 are going to take value 0. So now z's largest possible value is 8,000 divided by 3. So from the last system of equations, I can easily see that the optimal objective value of my linear program is at most 8,000 divided by 3. And the last system of equations, we obtain a solution that gives us an objective value of 8,000 divided by 3. Hence, the solution that we obtain must be optimal to the linear program that we would like to solve. So this is another sort of like a more scientific, more sophisticated way of ensuring ourselves that the solution that we obtain in the last iteration is optimal to the linear program. But again, for those of you who can just say, look at the objective function coefficient rho, if all decision variables over here have negative coefficients, then if I increase this decision variable, the objective value is going to go down. If I increase the decision variable, the objective value is going to go down. So I can conclude that there is no decision variable that I can increase to get to a better objective value. So I can conclude that I reached the optimal solution. Okay, good. So if you didn't really follow this last argument, that's also perfectly fine. Okay, so this is the simplex method to solve large linear programs. In the next lecture, we're going to do another example to get the mechanics of the simplex method really well. And also in the next lecture, as we do the another example on the simplex method, we're going to see a few other interesting things that can happen within the context of the simplex method. But we're going to get very comfortable with these kinds of mechanics very, very soon.